Why does a freshly cut apple turn brown within minutes while an uncut apple stays bright and innocent? That sudden familiar darkening is not magic or spoilage in the dramatic sense. It is chemistry happening in plain sight, and inside that chemistry lives a tiny drama of enzymes, air, and cell walls. In this video, we will follow a single slice of fruit from crisp white flesh to dull brown stain, and along the way we will meet the microscopic cast that decides fate. Enzymes called polyphenol oxidases, the phenolic molecules they act on, oxygen sneaking in, and the fruit's own chemical defenses. Our journey begins with a simple puzzle. If the fruit already contains the chemicals and the enzymes, why doesn't it brown while the skin is whole? The answer is living cells. Intact cells keep enzymes and substrates separate, like two teams in different locker rooms. Cutting the fruit breaks the walls, lets the teams mingle, and the reaction ignites. To make that clear, imagine a factory where raw paint is kept behind a glass door and mixers are locked in another room. As long as the doors hold, nothing happens. Cut the glass, and an excited mixing machine meets a bucket of pigment, and suddenly everything gets colored. That is the essence of the browning reaction. Now let's unpack the players and the mechanics. Polyphenol oxidase, or PPO, is an enzyme that loves to strip electrons from phenolic compounds. When PPO meets phenols in the presence of oxygen, it converts them into reactive molecules called quinones. Quinones are unstable and sticky. They rapidly link together into longer brown polymers that we recognize as the brown stain on cut fruit. The speed is astonishing because enzymes are catalysts. They do the job fast and then move on, letting a little damage cause a big visible change. Oxygen plays a decisive role. Without oxygen, the chain stops. The reaction is called enzymatic browning, and it requires molecular oxygen to accept electrons. That is why vacuum-packed or nitrogen-flushed fruit stays paler longer. If you block oxygen, you slow browning, but the story has depth. Fruits evolved this chemistry for reasons that help their survival. Many plant phenolics serve as anti-herbivore and antimicrobial defenses. When tissue is damaged, plants want to make the wound less tasty and less hospitable. Turning wounds brown and sticky can deter insects and slow infection. In a way, browning is a plant's emergency barrier. Messy but functional. Knowing the mechanism gives us several practical levers to stop or slow the process. Chefs and home cooks have used these levers for ages, sometimes without knowing the molecular names. Acid lowers enzyme activity. That is why lemon juice keeps apple slices pale. Salt and sugar change the local environment and can inhibit enzymes. Blanching, a quick dip in boiling water, denatures enzymes by unfolding their structure. Refrigeration slows molecular motion and slows the reaction. Excluding oxygen by submerging fruit in water or using vacuum packaging reduces the reaction rate. Now let's walk through a mental experiment with visual metaphors to lock the intuition. Picture the cut fruit as a stadium where fans throw colorful powder when teams meet. The phenolics are colorless powder. The enzyme is the person who sets off the powder cannons, but only if the air has oxygen to make the powder stick. If you remove the oxygen, the cannons can't fire. If you cool the stadium, the audience moves slower and fewer cannons go off. If you acidify the air, the mechanism jams. These metaphors show why acid, cool temperature, blanching, and oxygen exclusion all work, yet they work in different ways and with different trade-offs. For example, acid like lemon not only inhibits enzymes but can also change taste and textures. Blanching kills enzymes but also cooks the fruit slightly. Vacuum sealing preserves color but also changes how fruit breathes. Beyond kitchen tricks, food industry scientists and agricultural engineers have devised clever solutions. One ingenious approach uses modified atmospheres in packaging to keep oxygen levels extremely low while maintaining appropriate carbon dioxide to prevent off flavors. Another method is to use ascorbic acid, vitamin C, which acts as a sacrificial antioxidant. Ascorbic acid preferentially reacts with oxygen or quinones, reducing them back to non-colored forms before they polymerize, so it buys time. There are also naturally low PPO fruit varieties created by breeding or biotechnology. For instance, Arctic apples were developed to suppress PPO activity so the slices remain pale without additives. That raises interesting ethical and regulatory questions, but it also shows how understanding the mechanism lets us redesign outcomes. Let's zoom deeper into the microscopic choreography to appreciate why some fruits brown faster than others. Browning speed depends on three main factors: the concentration and activity of PPO, the amount and type of phenolic substrates, and the ease of oxygen access. Bananas and apples brown quickly because they have abundant phenolics and active PPO near the cut surface. Citrus, with its high acidity and different phenolic profile, browns far less. Avocado browns quickly, but the products are different and often result in slimy textures because of other enzymes and lipid oxidation. Textures and water content also matter. A juicy fruit has more mobile molecules, making reactions faster. Rinds and skins act as barriers. That is why a whole apple can stay pristine on a table for days while the sliced interior turns the moment the knife passes. This understanding lets us predict outcomes in surprising places. Think of coffee. Coffee beans contain phenolics and enzymes too, but the roasting process denatures the enzymes and converts phenolics into new compounds, so the browning story is quite different. Or think of potatoes. Potatoes will darken when cut because they are rich in phenolics and PPO, and their earthy taste also changes because of enzymatic and microbial processes. Now for an exploratory experiment you can try at home to see principles in action. Cut 3 identical apple slices. Leave one exposed to air. Squeeze lemon juice on the second. Place the third into an airtight zip bag with a small packet of ascorbic acid or a bit of crushed vitamin C tablet and squeeze the air out. Observe every 5 minutes. The exposed slice will darken fastest. The lemon-treated slice will stay pale the longest initially but may develop some texture change. The vacuum plus ascorbic acid method will also preserve color for a long time. This small test visually demonstrates enzyme activity, oxygen's role, and the protective power of antioxidants and acidity. Let's pause and look at a surprising wrinkle. Not all browning is enzymatic. Non-enzymatic browning, such as the Maillard reaction or caramelization, produces brown colors through different chemistry and often requires heat. The Maillard reaction between sugars and amino acids gives browned bread and roasted coffee their flavors. That chemistry is delicious rather than defensive. Enzymatic browning is cold, fast, and often unwanted for fresh produce. Knowing which reaction is at play helps choose the right fix. Before we reach the Eureka, consider scale and timescale. Enzymes act very fast at the molecular level, but visible color change requires many molecules to polymerize. That is why a tiny cut might slowly darken, while a larger cut goes brown quickly. More broken cells mean more substrate and faster aggregate reaction. Temperature sensitivity is another practical insight. Storing cut fruit chilled at refrigerator temperatures can dramatically slow browning, but does not stop it unless combined with other techniques. Now for the moment when everything snaps into focus. The browning of cut fruit is not a single villainous process, but a predictable cascade you can read, control, and even harness. It is the visible trace of a living plant's chemistry reacting to injury. It is defense, chemistry, and physics layered together. If you want fruit that stays pale, you do one or more of 3 things. Keep enzymes from meeting their substrates, remove the oxygen the reaction needs, or use sacrificial chemicals that intercept reactive intermediates. Those are the universal levers. Finally, what does this knowledge change for you beyond keeping fruit pretty for a salad? It connects everyday kitchen behavior to broader themes. How organisms use chemistry to protect themselves, how humans have co-opted those mechanisms for food storage, and how minor tweaks in environment produce large visible effects. It also shows how scientific understanding gives you elegant, minimal solutions instead of guesswork. If this short chemical story made your next apple slice feel like a tiny laboratory, then mission accomplished. Try the 3-slice experiment, and when you take that bright apple bite, enjoy not just the flavor but the invisible chemistry you briefly paused. If you like this unpacking of a familiar miracle, press like, share it with someone who chops fruit every day, and subscribe to How It Actually Works for clever explanations that give you the key to everyday mysteries. We break down the small mechanics so you can see the world differently, one simple question at a time.